Lesson 1.2, understanding limits graphically and numerically. So we have three big topics in calculus. Limits is one of them, okay? This whole first unit will focus on limits. And we'll have several units on derivatives and several units on integrals. If we look at what it says here, limits are the backbone of understanding that connect algebra and geometry to the mathematics of calculus. In basic terms, a limit is just a statement that tells you what height a function intends to reach as you get close to a specific x value. Recall from pre-calculus that you evaluated three types of limits and complete the table below. We did a little bit with limits in pre-calc. We didn't do a ton, but we did have a little bit. So when we talk about limits, there's proper notation, proper ways to read it. You can have a right-hand limit, which is the limit as you approach from the right side of that value. You can have a left-hand limit, which is as you approach from the left hand of the value, or you can just have a general limit, which would be approaching from both sides of a set value. So proper notation, and I'm going to use c as my value here. So the limit as x approaches c from the right of f of x. So what that is, you have limit as x approaches c plus, as in it's a little superscript, like exponent almost, but that plus says from the positive side. Well, the positive side is the right side, right? And then f of x is of the function. As opposed to the left-hand limit is the limit as x approaches c minus. So notice it's not a negative c.
Is f of x also like a subscript?
No, f of x, and that's why I was going to try and write this one better. So limit and f of x, limit and x approaching c are above each other.
Oh.
F of x is like the whole thing.
All right.
Okay.
Got it.
And then the final one is just the limit as x approaches c of f of x, of the function. Okay, so f of x just represents whatever function, graph, whatever we're talking about. As x approaches some value, that's as x approaches whatever value, x value they give us there. So a plus after the c means approaching from the right, approaching from the positive. A negative after the c means approaching from the left side of the value. And just a plain old value means approaching the value from both sides. Okay. Verbally, these are all going to kind of be the same, but this is the limit as x approaches c from the right. You could also write it as x approaches c from the positive side. Generally, we say from the right, though. That means this next one is the limit as x approaches c from the left. And then the bottom one, of course, is just the limit as x approaches c. And part of what we're going to do, part of the reason these notes, some of these notes do go really quick, is we're just examining some of these limits. So some things will go quicker than others for sure. Okay, get what you need from there, and then we'll look down at example 1. We're going to analyze a rational function and examine the graph here. Okay, so example 1, use the equation for f of x and the graph of the function to analyze completely. So f of x is 3x squared minus 8x minus 3 over x squared minus 9. Notice first thing in the box it suggests doing? Factor and simplify. Well, let's ease you in. Can you factor the denominator?
Yeah.
X squared minus 9. What do we know about x squared minus 9?
Yeah.
Sound familiar?
Mhm.
That's the kind of thing you pick calc now. I kind of assume that that's old news. You might need a reminder. It's day 1, I know. Now, the numerator.
If you do that, you gotta teach me how to do that
Yeah,
one.
I'm just kidding.
I don't remember it.
I don't remember it either. Actually, I remember pre-calc.
I have to reteach myself
We
that
spent
one.
5 to 10 minutes on trying to figure it out, and it just didn't work for anybody.
I do PAC.
Okay,
Casey.
so Proctor AC, here's what I'm going to do actually. Follow. I'm just going to do a guess and check. So, what does 3x squared have to break into? I mean, what's pretty much the only option?
X and X.
2x and x.
2x and 1x? Or 2x and x?
3X.
3x and 1. 3x and 1x. There we go. Now we're good. It just took me just a second.
We have totally forgotten how to FOIL here. So, remember, we're looking for what two pieces multiply to be 3x squared.
Oh.
So that would be 3x and x. That's my horrified face when we're saying x and 2x. I'm like, okay, guys, come on, process here. Are you with me on the 3x and x now?
Yes.
though? Took a moment, but we're there. Now, and the reason I'm just doing a guess and check on this one because 3x squared, you only had one option, yes?
Mhm.
Okay, now look at the back term, 3. What does that have to be?
3. Well, 2 and 1. No.
No.
3 and 1. I was right the first one.
Okay, some combination of 3 and 1, yes? Now, this is where you have to do a little thinking. It could either be 3 and 1 or 1 and 3. One of them is going to have to be a negative. I'll get to that here in a moment. 2 things. First of all, there was no GCF up there, was there? I, as your teacher, know it can't be 3 here and 1 here because that would create a GCF. And if there wasn't a GCF up there,
That can't be
there's not going to be a GCF down there. So that is going to force it to be 1 and 3. Is it always this easy with all of them? No. But this is one that it is.
I don't understand this method. I don't think I've ever done it this way.
Okay. Then product of AC, I mean, it's just guess and check. It's just not going through the big old long product of AC method. For me, this is quicker than product of AC
Mm-hmm.
because I can just kind of, okay, 3x squared has to be 3x and x. Oh, 3, that has to be 1 and 3. Now, where's this negative 8 come from? This negative 8 comes from your outsides and your insides. Well, my outsides are going to give me 9x. My insides are going to give me 1x. Could those make negative 8 if signs put in properly?
Yes.
So what are my signs going to be?
-1.
-3, +1.
What? Because I need it to be negative 8,
Does.
I'm going to need a negative 9x
Oh.
and a plus 1x.
Okay.
We'll do product of AC at some point too because we probably need to review that. But and I'll go back and remind myself of how slip and slide works so I can use that if we want. But slip and slide was a method that Mrs. Rogers learned that she then showed me and I thought was kind of cool. So we talked about it in at least one pre-calc class. So okay, we factored. Now what?
We can cancel those out.
We can cancel, can't we? So we can cancel
X plus
X minus 3.
x minus 3. So 3x plus 1 over x plus 3. Obviously, you could have foiled that numerator back together to make it work, right? Which is kind of, in a way, what I did. I just did it in pieces. Okay, are we somewhat okay with that?
Mhm.
You know, it's rough, I know. First factoring of the year. Okay, coordinates of the whole. What all do we have here? Coordinates of the whole, domain, range, vertical, horizontal asymptotes. Okay, so you're looking at a graph. What are the coordinates of the whole?
3. What?
There's a decimal. There has to be.
that'd be positive 3. 1.75.
Like,
Wait a second.
yeah, 1.8 maybe.
Am I looking at the wrong thing?
Yeah.
Oh, that hole. I was
Is
looking
there
at
another
the
one?
asymptote.
I'm guessing she was looking at something in her brain that was saying it was a hole, but it's not really a hole.
Yeah.
There's only one hole, but by Emma's question, I knew that she was looking at the wrong thing.
I was looking at the asymptote. I have
Okay, fair enough. I'm trying to figure out if there's a way we know there is a way we know. Okay. We can agree the x value is 3 here, yes? We were provided an equation, yes? Could we plug in x to find the other part? Now, you do you. You can do the original equation, or what could you also do?
3x plus 1.
Factored equation. So I can do f of 3. It's 3 times 3 plus 1 over 3 plus 3. .75, 1.8, not far off, but
Not close enough.
I'm looking for a 1.6 repeating,
Yep.
which is better written as 5/3. What'd you do wrong?
Oh, there we go. Found it. Never mind.
I'm like, you did
all
something
good, all
wrong if
good.
you didn't get that. I don't know. Okay. Now, a little bit of vocabulary. So a hole, do you guys remember our discontinuities here? This is one of our discontinuities. And it is a removable or non-removable?
I don't
We have
remember how to
50-50
figure it out,
chance.
but I'm guessing removable.
Removable.
I was gonna say non-removable.
I'm gonna say non.
It is removable.
Yeah, guys.
Dang
Yeah.
it.
Yeah.
Okay, and I was trying to figure out what I have written in here. First of all, you will, in this calculus curriculum, they also sometimes refer to it as a point discontinuity. So you might see it as a point discontinuity, or you could see it as we learned it as a removable discontinuity. Either way, it is definitely a discontinuity. Sorry, that's one of those words I can't just spell. I have to think as I go there. So whether you would call it a point discontinuity or removable discontinuity, interchangeable vocabulary there.
So, what is not removable?
We'll get
Is
there.
that-
Oh,
Okay.
Hold that thought. I'll get there. Okay? Let's talk about our domain.
I mean, it's x values, isn't it?
Okay? Domain is x values, right?
So,
So in terms of x values, my x-axis, right? So we're looking from left to right. So as we start our graph, where does our graph start on the left side?
Negative infinity.
Okay, it's going off there, right? So it's going to start going off to the left, negative infinity. Now, as we look here, we obviously have a break here, yes?
Yeah.
Because it's not connected. So where's that first break going to be at?
-3.
And why -3?
Because there's an aspect
Because
right there. Right there.
Okay, you with me? So our first part of the domain is negative infinity to -3. Take a break because there's an asymptote, right?
Is it a comma or do you do the U?
I have a comma in my notes. You could do a U also, though, I think. Okay, where does my graph pick back up?
-3. Well, negative infinity.
-3.
It picks back up on the other side of the asymptote. The y value is negative infinity. I'm not talking y values,
Oh, right. X value.
x values. So it goes off to negative infinity. It takes a break as it approaches -3. It picks back up on the other side of -3. You're saying -2 because you're just seeing what it looks like, but know the graph behavior. What's it going to do as it approaches an asymptote?
Get closer.
It's going to get closer and closer, okay? So we're always using -3. Notice I used a parenthesis with -3 because is it ever going to touch -3? No. Comma. Okay, where's the next break?
3.
3.
Oh, we have a hole here, don't we? So we're going to take a break at 3.
Oh, crap.
At 3, we're going to use a...
It's going to be a
Bracket.
bracket.
No, it's a parenthesis because it's an open hole.
Is it going to touch 3?
No.
No, there's a hole there. I'm sorry, I was laughing because I turned around like the majority of you were erasing, so it made me laugh. Okay, so we approach 3. We approach this hole from the left. You can't keep drawing at the hole. You have to pick your writing utensil up and continue on the other side, yes?
5/3.
So now where do we start?
3.
5/3.
3. We're still using x value. We're still using x values.
Oh yeah, that's why.
So it's just like the asymptotes. It doesn't touch 3, but it's on both sides of 3. And then where?
Infinity.
Positive infinity. Oof,
That was rough.
that was rough. You did this last year,
That's
though.
why it'll be so much easier now.
Okay,
You tell them.
now range. I don't know that I'd say y will be easier, but
Why is never easier?
okay. I don't think it's, well, yeah, we'll talk about it later, I guess. Range. Range is y values, process of elimination. So domain was x, so left to right. Range is y, so
Down to up.
down to up. Sounds weird. I know we want to say up and down, but down to up. So, where's my graph begin as we start down here?
Negative infinity.
This arrow right here indicates that it's going down to negative infinity, because now we're just talking y values. Now, as we're going up, where is the first break?
3.
Yeah, no,
5/3.
5/3.
No, it's the asymptote.
Wouldn't
It's
it
3.
be-
It's 5/3.
No,
No,
it's
the whole is
5/3 because the
5/3.
whole.
Why wouldn't it?
Because we have.
We're not to the asymptote yet.
Wait, wouldn't it stop it? It would stop at 5/3.
Where it was.
Okay,
The
so
hole in the line. You know,
Oh,
stop it.
oh no.
we're talking about right now. Okay, so this graph is going,
Gone.
and then right there, it doesn't exist. It's gone. What is the y value at that point?
5/3.
5/3. So negative infinity to 5/3.
This is
Where do I pick up back?
5/3.
Right above 5/3, right? Right below 5/3 we stop. Right above 5/3 we pick up. How far do we continue going up?
3.
We're going to be approaching 3. Are we going to touch 3?
No.
No, because it's an asymptote. It is 3, isn't it?
Yes.
Yeah, horizontal asymptote is 3. Sorry. Where do we pick back up?
3.
We're over here on the left, yes. But it's the y value is the top side of 3, not 4, right? It looks like 4, but you have to think, oh, it's an asymptote. 3 to infinity.
Yes.
It's just starting remembering.
Better than last one.
Okay, vertical asymptote. What's the equation for the vertical asymptote?
X equals -3.
What?
Sorry. X equals negative 3.
Yeah.
Where's my vertical
Oh,
Oh,
yeah.
the asymptote.
asymptote?
And then why would you?
So, and vertical lines are always x equals a number because it cuts through the x-axis at -3. Horizontal asymptote?
Y equals 3.
Horizontal lines are always y equals, and it is up at +3.
That's where I got my.
Let me backtrack to Doug's question. I thought it would come up somewhere, but it didn't really. So a removable discontinuity is a hole. A non-removable discontinuity is a vertical asymptote.
Oh.
Okay, so now we called it a non-removable discontinuity. You will also see in this curriculum an infinite discontinuity. Okay, so it could be infinite, or it could be non-removable.
That's only the vertical.
Yes. Because when we talk about a function being continuous, we're just talking about in terms of x values. If something is continuous, it's in terms of x value. Can you start at the left side of your graph and trace all the way to your right side?
What makes it removable and non?
A removable is a whole, non-removable is a point. It's just the vocabulary that goes with it. Okay, so right here it's because it was a whole. Here it's because it was a vertical asymptote. Okay. We got everything? Whew. We're shaking the cobwebs off, right?
Yes.
Slowly but surely.
This is 1.2 and 1.3.
No, within each lesson they have topic pieces. This lesson is like 6 pages altogether. So you're going until you see the 1.2 homework. This lesson goes through page 12. Thus, we gotta keep moving. Okay, understanding limit notation. So this is kind of, whoops, I'm on the wrong page. How we are going to write our limits. So we did a little bit with limits in pre-calc, not a ton, but we did a little bit. We are going to look at how we use our notation here. Okay, so you have the graph. Is this the same graph as previous? It is, isn't it? Yeah, okay. So, as x approaches negative infinity, the graph of f of x approaches what? So, as in the x values, you go infinitely left. What is your function value approaching? Or when we talk about what is that function value approaching, that's what is your y value approaching. So as you move left, what is the height of your graph approaching?
Negative.
Infinity.
No.
Wait, that would be approaching 3.
That one I
Oh
can
yeah,
get on
because
board
that's
with. So because what's happening? As my graph goes left, so I'm looking at this piece here. There's as x is approaching negative infinity, as I go towards Mr. Stanley's room. What y value am I getting closest to? That asymptote at 3. Now, officially, how is this notation written? And that notation is officially written, the limit as x approaches negative infinity of f of x is equal to 3. Okay, that's the official notation that you'll need to get in the habit of writing. Okay. Okay. As x approaches infinity, what is the graph of f of x approaching?
Negative 3? No.
So as x goes to positive infinity, so that's as we go towards Miss Minnick's room, what y value are we approaching?
3.
3, except from the bottom side, yes? But we're still approaching 3. This time it's going to be 2.9, 2.99, 2.999, 2.999. However many, you know, whereas over here, we're getting closer, 3.1, 3.01, 3.001. We're getting closer from the top side. Okay, so if we write this, the limit as x approaches positive infinity of f of x, that's the limit we just answered, and it is equal to 3. Okay, look at the next one when you're ready. As x approaches negative 3 from the right, the graph of f of x approaches what? So as x approaches negative 3 from the right.
Negative infinity.
So negative 3 is my asymptote, yes? As we approach it from the right, where's my graph going?
Oh, negative infinity.
Down to negative infinity. Is that making a little bit of sense? Now, if I write this for notation, it's the limit as x approaches negative 3 from the right means I'm going to put
Plus.
a plus after it of f of x is equal to negative infinity. Okay. As x approaches 3 from the left, so that's my asymptote, yes. As we approach 3 from the left, that means I'm following this piece, which is going where? Positive infinity. So the limit as x approaches 3, wait a minute, wait.
Is it 3 or negative?
No, it would be approaching.
I just did -3. It doesn't say -3. It says +3. So I totally screwed up.
What?
We just did -3 from the right. What did my brain now try to do?
Negative.
-3 from the left. Is that what it's asking me to do?
No.
No.
3.
I led you astray. My apologies.
Just negative.
So as x approaches 3 from the left, so where is 3?
3 is
3 is the whole. As we approach that from the left, what y value am I approaching?
5/3.
There we go. Are you with me?
No.
My apologies. So as x approaches 3 from the left, means I put a negative after it, of f of x equals 5/3. Ah, I should have gone down. That's what I should have done. Oh well. Because now, as negative x, or as x approaches -3 from the left, oh yeah, of course. What is it? -3, which is my asymptote from the left. That is positive infinity. I'll go with you there. So the limit as x approaches -3 from the left, means negative afterward, of f of x is equal to positive infinity. And one last one. As x approaches 3 from the right, what are we approaching?
5/3.
You guys with them?
Mm-hmm.
As we approach from the right, we're approaching that whole of 5/3. So the limit as x approaches 3 from the right of f of x is 5/3. Okay. They ask, can you explain what the value of a limit represents in terms of the graph? Okay, the value of the limit. What were all of our answers essentially? We did as x approaches some x value. Then all the answers we gave were y values, right? So the answer to a limit is always a y value. So the limit is the y value that the graph is approaching from both the left and the right side of the target value, or whatever the c value is. Let's see. Limit can also occur at a whole, which is a removable discontinuity, or approach an asymptote or infinite discontinuity. I'm more concerned that what's the value of a limit represent in terms of the graph? It is the y value. Okay, so I guess what I would think about is the answer to a limit is the y value. That's what I would think about. Okay. Before I turn the page, informally, a limit is a y value, which a function approaches as x approaches some value. The limit as x approaches c of f of x equals L means as x approaches c, f of x approaches the y value of L. And that, of course, is assuming L is a real number. Okay. Moving on. There's a lot. Consider the function shown at the right. It's a fun function. Say you want to find the limit as x approaches 4 from the right of f of x. The positive sign of the limit notation indicates a right-hand limit. I already talked about this. If you think of the function as a highway and imagine you're traveling along the graph of f of x towards x equals 4 from the right, not to the right. And you stop at the vertical line, x equals 4. The y value where you stop is 3. Therefore, okay, the limit as x approaches 4 from the right is 3. So are you with this?
Yes.
So find as x approaches 4. So here's 4, yes? As we approach 4 from the right. So as we approach 4 from the right, what y value are we approaching? And that is the y value of 3, right? That's what they're saying there. Now, we're going to answer a whole bunch of different questions here. Get all of our notation straight. First one, what is f of 2?
One.
What?
Disagree.
Negative.
How do you figure that out?
So I want to know what is the value of this graph when x equals 2?
Negative 1.
Where is x equals 2? Here's 2, yes. Where does the graph exist?
-1.
At -1. Common wrong answer is the one that Doug gave me. Do you see why the one is the mistake?
There's a hole there.
There's a hole there. The graph does not exist there. I'm looking for where the graph exists. Got it? Okay, let's go over to B. F of -1.
4. 4.
Yeah.
Yeah.
Why do I have that there? Okay, oh well, moving on. Okay, the limit as x approaches 4 from the left side of f of x. You guys with her? 4 from the left. You go to the y value of 3. Stop me if you don't like an answer.
Hold on, you just gotta give me.
No, how does that work?
I just-
why would
I
you
need to
come the
comprehend
like the
it.
all the way on the left.
I just need to comprehend.
Okay, we can't go all the way to the left or we're just wasting a bunch of time. If we go all the way to the left, okay, we have to trace here, jump here. I just want to know at 4. All I care about,
Okay.
4 was the number they gave me.
For some reason, I was thinking -4.
4 is the number they gave me, x value of 4. How do I get to that point? How do I get to where the graph exists at 4?
3 up.
I'm at, or it's basically, as I approach that, what value am I at there?
Now I got it.
Okay, which I need to be careful about as we approach, because there are some catches on this. Okay, what about as x approaches 2 from the right?
Negative.
Mm-hmm.
I don't know.
From the right?
Which way is our right?
I thought I meant from the left because there's a negative. I'm going down.
I'm on D.
Oh, it's 2.
Okay, so here's 2. As we approach this value, right, as we approach 2 from the right. So all I have to look is right before 2, what y value am I approaching?
1, but there's a hole.
But are we approaching that value?
Yes.
Okay, a limit does not mean it has to exist at that point.
Okay.
Okay, a limit does not mean it has to exist. It's just approaching that. Okay, we can't say we're approaching -1 because the graph doesn't get me there. From the right, the graph gets me to 1. Yes, it's a hole, but a limit, the value does not have to exist as a limit. It just has to approach that point. Clarity? Okay. Limit as x approaches 2 from the left.
Negative.
Are you with me there? So here's 2. As we approach from the left, we are approaching the y value of -1. Too many negatives and positives, guys. Okay. As x approaches -1 from the right.
2.
Here's -1. From the right means I'm tracing right up there to 2. So I have to get rid of some of these marks. Too many marks make it. Okay. As x approaches -1 from the left. So here's -1. As we approach from the left,
Is it also
2.
2?
it is also 2. And here's the deal. It makes sense that it's 2 because as it approaches from both sides, it approaches that same point there, right? The graph is connected, it approaches the same point. Does this 4 mean anything in terms of
Yeah,
limits?
Is that just there?
No.
It's just chilling.
That right there is f of -1 is equal to 4.
Okay.
But that will never be the answer to a limit because the graph never connects to it.
That makes sense.
Okay, it can be the answer to what the function value is, but it's not going to be the answer to a limit. Okay? As x approaches -4 from the right. Yeah, because here's -4 from the right. We're still at that horizontal level of 2. Okay. As x approaches -4 from the left.
Yeah, we're just so too.
Because the graph
No.
exists there.
From the left.
Would it be 0?
No. Okay, so we're trying to approach -4 from the left. What's the problem?
It doesn't exist.
My graph doesn't exist left of -4. The farthest over it exists is at -4. It doesn't exist at -4.1. Okay, so on and so forth. So this limit, DNE, does not exist. Common abbreviation you're going to see me always write is DNE. Are we okay with that?
Yes.
I'm pretty sure it's a DNR.
No, DNE, not DNR.
Or DO.
Okay, the limit as x approaches -1 of f of x.
2.
We kind of already answered that. What was the limit as it approached -1 from the left?
2.
2. What was the limit as it approached from the right?
2.
2. So guess what it is when you connect them?
2.
It goes right there, it right there, it meets at a point. That point is 2. What about the limit as x approaches 2?
Plus or minus 1?
Nope. It approaches 1 from the right, -1 from the left. Are those values the same? No. So,
Doesn't exist.
1 -1.
DNE does not exist. This limit does, in order for that limit to exist, it has to be the same value on left and right. And that goes back to, what do I want to say? That goes back to part E. And we did the other one, part D, right? That goes back to those two. Those two were different answers, so this answer does not exist. Okay, are we ready for L?
-2.
Limit as x approaches 5.
Or just a -2.
That's the values.
But it's continuous.
It's not even on there.
Yeah, but it's the point is still there. Even though it continues
There's
through
an
it.
arrow.
Even though it
Make it
continues,
continuous.
it continues through there. So from both ways, it'll be approaching -2.
So a difference from the left. The left was an endpoint. Graph is done. Finito. What is happening over here? That line continues straight because there is an arrow. So if I extend it as the graph is showing me,
That's right.
as x approaches 5, what y value are we approaching?
-2.
-2. Have I sold it? Okay. As x approaches 0,
-1.
you with me? Right here, right? Here's 0. So that's approaching this point from both sides, which is -1.
Is the next one -2?
I don't know. I haven't looked that far ahead. As x approaches 1. Yes, because it's right there. Yes? Okay. Getting better with limits?
Maybe.
Okay.
Just critical thinking.
If we think the function of the function as a highway, then the point at 2, -1 could be considered the end of the road, while the point at -1, 2 is more like a pothole. How would you describe the points located at 2, 1 and 4, 3? Okay, so let's see. 2, -1, end of the road, yes? Okay. What else did they have? -1, 2, pothole, because the road keeps going, but there's a hole in the road, yes? Okay, what about 2, 1?
The side of the cliff.
What was it? It was 2, 1.
I mean, it would be. I mean, you have no road and you have a hole.
Well, okay, so
It could be a boat ramp.
What I have written in mine is dead end without a barrier. So side of a cliff,
Like,
equivalent thinking. I mean,
it's the same thing, basically.
yeah. So I have written is dead end without a barrier. In other words, the road ends there. And why are we saying without a barrier?
Because it doesn't pick back up.
Because there's nothing to stop it.
There's nothing to stop it. It's a hole. And what about 4-3?
Almost a switchback curve.
Just a little curve in the road. Sharp turn. I like
oh,
sharp
you
turn.
know, out on,
A mountain.
Hairpin curve.
where's it at? That's a stop sign, I would say. Out on
But you can't roll that
28
stop sign.
in Tipton
Trying to figure out.
towards Atlanta.
Oh.
Sharp curve, I'm with you guys. I get it. Sharp turn. What? I have bump in the road written down.
Interesting. I mean, it could be a bump in the road if you just blow that stop
Bump
sign.
in the road and it makes you go right,
Yeah.
back down.
I mean,
I was thinking mountain.
But it's a road. We're traveling on a road. That's not how high it's going.
That's what
This is a path. So, I don't know.
sharp turn.
Sharp turn. Mine says bump in the road.
5 mile per hour turn.
Yeah.
10 if you're beyond.
I don't know. Why did I put bump in the road? I'm trying to remember. I guess maybe because the point is there. Bump in the road. For convenience, I'm just going to say sharp turn. You guys had all your other descriptions. It's good. Moving on.
It just keeps getting more and more notes, it feels like.
Some of the notes are really long. Some of them are really short. It just, as I said, it's rare I can get notes done in a day. So I'm pushing things. I really want to. Okay. Limits
That's a heartbeat.
can fail to exist in 3 situations. Okay? Case 1. Justify why the limit does not exist at x equals -1 for this function. Well, what's happening at -1?
There's 2 holes.
2 holes, and most importantly, they're not connecting, right? And so here's the deal. For this limit to exist, the left has to equal the right. And so, like, if we look at, so the limit as x approaches, what are we doing? -1 from the left. That turned into a backwards 7. Yeesh. What is the limit as x approaches -1 from the left? -1. Okay. What is the limit as x approaches -1 from the right? +1. Here's the deal, guys. The limit does not exist at -1 because the limit from the left does not equal the limit from the right. Good AP vocab here is saying the limit as x approaches -1 from the left of f of x does not equal the limit as x approaches -1 from the right of f of x. That is, we'll talk about that as we go through the year, but that's good AP vocab. We're proving that limit does not exist. Now, if I go back up and fill in one, limits differ on the left and right is the case. Okay, limits differ on left and right. So thus the limit fails to exist. Okay. Ready to talk about the heartbeat?
Yes.
No.
Okay. The heartbeat, which I'm actually going to call this one oscillating behavior.
Alright.
And I believe this is a good one to graph on your own because I don't think this graph does it justice if I recall. But I believe what happens, and did I write it down? But if you really zoom in, I don't think it actually connects.
Can I use
to move yours really fast?
Yeah.
Oh, I'm
So yeah, there's an equation there.
I
If you
wanted to
graph
be-
that, and what you're going to want to do is then you're going to want to zoom in. What is it? Sine of 1 over x.
Mhm.
So I'm just going to do zoom 6 to start me off.
I think I'm doing a Z-box situation, I'm pretty sure, right?
That's probably a smart idea. I was just going to zoom in. Zoom in actually shows it relatively well.
Don't do zoom fit.
Okay, good to know.
Well, I mean, it's.
So this was me. I graphed it once, and then I zoomed in once. Put a piece of paper under that so it won't be. It's just, and mine's really blurry. It's being annoying, but that was just zooming in once. What do you notice?
There's a super zoom in.
On the right, it ends up by positive 1-ish. On the left, it ends up over by negative 1-ish, doesn't it?
Oh, I see it now, yeah.
Okay? So, oscillating behavior, just because it oscillates doesn't mean it connects there. And so that is more of a by inspection. If you zoom in and look really closely, one side is greater than 0 and the other side is less than 0. And I think what I'm going to say is the limit as x approaches 0 from the right of f of x, without taking the time to investigate, we can say it is greater than 0, yes? It ends up on the positive part of the y-axis.
Yes.
Whereas the limit as x approaches 0 from the left of f of x ends up down in the negatives. So we can say it's less than 0. Okay? So you've got one above, one below. I'm going to say, therefore, does not exist. 3 little dots mean therefore. Are we familiar with that?
No.
That's a good one to use for calc too.
Are they just like in a triangle shape?
Yeah, just 3 little dots in a triangular shape mean therefore.
Looks like a little like cult symbol or something. I'm not sure.
No. AP Calc's cult symbol, I guess. Okay, and example 3. Oh, I don't like this one. Okay, so this is, case 3 is called unbounded behavior. And it's a technical catch, which is why I don't like it. Okay, justify why the limit does not exist at x equals 2 for f of x. Well, what would you say the limit is doing? Because I know what I would say.
It's an asymptote.
It's an asymptote, and what is the graph doing on the left and on the right?
Going towards infinity.
Going to positive infinity, yes?
Yeah.
So here's the deal. Officially, I guess unofficially, I would say the behavior, the official behavior there is it approaches infinity. Officially, we say the limit does not exist because by definition, infinity is not a real number, and a limit has to equal a real number. We're getting technical here. Okay, so this is the one where I was going to write it down there, but I don't really have room. I'll squeeze it right here. Gosh darn it, or I won't. The limit as x approaches 2 of f of x does appear to equal infinity, but that is what we can say is the behavior. Okay, the behavior of the graph goes to infinity. However, the official limit, I think, I don't have it written down, but I don't have it written, does not exist, but there's that technicality here of, is that limit really infinity? Can you say that? So what I'm going to say is, by definition, infinity is not a real number. And at the bottom of the previous page, I said something about L having to be a real number, the limit having to be a real number. I threw that in. This is the catch, okay? So by definition, it's not a real number. And so thus, infinity is a behavior. So again, it's generally speaking, we're going to say the behavior tends to infinity. Okay?
We almost got done.
I
One
know.
page.
I'm debating how I want to handle this because I don't want to spend a whole nother day on this.
This is like the little baby page. We can finish it real quick.
Okay, it's front and back.
I know, but like this. Oh no.
But
Ooh,
yeah.
it's a lot.
Now, I'm trying to remember what this piece was. Considering the function f of x, complete the table below to find the limit as x approaches 3. So this is you, and you're going to have a few of these in homework, filling in this table. And what we're going to use is we're going to use this information. What do I have? Okay. You know how to plug into your calculator, right?
Right.
You're not going to complain if I just tell you values?
Nope. Not even a little bit.
0.1265. 0.125. 0.1250 does not exist. 0.1249. 0.1248. 0.1234. Now, we're going to use a table here to find the limit. So look, we're talking about as x approaches 3, right? So as we go this way, and as we go this way. Does my graph have to exist at 3?
No.
No, it's a limit. What are we approaching from either side?
125.
0.125, yes? From the left, as x approaches 3 from the left. This is from the left, yes? We're approaching 0.125. As we approach from the right, well, it doesn't actually show it, but what could you assume? It appears to be 0.125. So what is this limit? 0.125. Okay? Because it didn't exist at 3, what is 3 going to be? There's going to be a hole at 3. Well, it could be a hole or an asymptote. Well, no, it can be an asymptote because then it'd be going to infinity or negative infinity.
Oh.
Make sense?
Yep.
Okay, guys. Here's what I want you to do. We have a page and a half I haven't done. Honestly, a lot of this next page is reading and explaining a little bit. All I haven't done is the back. Do the homework. Okay?
Oh,
I will decide after looking at things whether I want to go back and finish those examples or not. If I remember to get the key posted, the answer key for the notes will be there too. Now, do you understand where your homework is?
Until page 15, right?
Starts on page 13, right?
Ends on page 15.
And it goes 13, 14, 15. Because then lesson 3 starts on 16. Are we clear on this?
Yes.
I'm trying to help you guys understand until you get used to
Which is appreciated.
how this works. So basically you're doing page 13, 14, 15 for tonight. Some of it is the real easy stuff we did. Okay, I really think you can do most or all of this homework tonight.
All right.
Okay, do it.
Got it.
Tomorrow we'll either check it or finish notes and check it. I don't know. I need to sit and look.
you're ready for this?
Sorry, I have to do it.
No, that's all right. It's just like,
Sorry about
nope, you're fine. I just,